In the opening years of the Second World War, a new front was opened. This battlefield was not on land or sea, but 5 miles up in the frozen hostile skies over the Third Reich. Here, the air is too thin to breathe and too cold to survive. For an aircraft engine, it's a place where power goes to die. Bombers needed to fly in this realm to escape the deadly flak from below, but their engines would choke, starving for oxygen. The entire American strategy of high-altitude daylight precision bombing was facing a critical atmospheric wall. The British, with minds like Stanley Hooker, were perfecting complex 2-stage mechanical superchargers. The Germans relied on advanced fuel injection. But American industry, building on decades of experience with power plant turbines, chose a more radical path. General Electric, a company that built massive steam turbines, believed they could harness the engine's own fiery exhaust. The device they perfected was the Turbo-supercharger. It was, in essence, a tiny, incredibly robust jet engine bolted to a piston engine. Instead of being wasted, the 1,000-degree exhaust gases were channeled to spin a delicate turbine wheel at over 20,000 revolutions per minute. This turbine drove a compressor, force-feeding the engine all the air it could ever want. This single piece of technology was America's high-altitude secret weapon. It allowed a P-47 Thunderbolt to become a juggernaut in the upper atmosphere. It gave the P-38 Lightning the long legs and high-altitude punch to guard the bombers. And most of all, it allowed the B-17 and B-24 to form their massive self-defending combat boxes and fly into the heart of Germany in broad daylight. This mastery of high-temperature metallurgy and high RPM turbines was not just the key to winning the daylight war, it was a dress rehearsal. The knowledge forged in these turbochargers would become the bedrock of a new, even more powerful revolution, the dawn of the jet age.
Power and more power. Power to give pilots flying turbo-supercharged equipped airplanes many tactical advantages over pilots flying airplanes not so equipped. The turbo-supercharged airplane will outperform the unequipped airplane in almost every respect. It can take off with a greater margin of safety and with heavier loads. It can climb faster and higher. It can fly over bad weather and above the effective range of anti-aircraft fire. In many instances, our turbo-supercharged bombers, flying at high altitudes, have outperformed many pursuit ships. The gain in fighting power made possible by the turbo-supercharger will in many instances make the difference between a successful war mission and the death or capture by the enemy of yourself and your crew. The control of this bonus in power is simple, but important. And in order to make the best use of it, the pilots must be thoroughly acquainted with its performance and know how it should be handled. In preparation for flight, the pilot first unlocks the flight control. The co-pilot turns on the master battery switch. The pilot checks to see that the throttles are closed and the supercharger controls are off. The co-pilot checks to see that the mixture controls are in the off position. The co-pilot receives the all-clear signal on number 3 engine, starts the fuel booster pump, and switches on number 3 magneto. Then the co-pilot starts the engine and moves the mixture control to automatic rich, keep the engine running. When the oil pressure on number 3 is rising, the co-pilot receives the all-clear signal on number 4 engine. The co-pilot turns on fuel booster pump and switches the ignition to both. Then he starts number 4 engine. He also moves the mixture control to automatic rich and signals when the oil pressure is okay. When starting engine number 2, the pilot receives the signal from the mechanic and signals the co-pilot that number 2 is all clear. The co-pilot then turns on the fuel booster pump and switches on the ignition and starts number 2 engine. and number 1 is started in the same order. The engines are warmed up until the oil approaches normal temperature. Excessive ground running is undesirable, as it may cause rapid burning of ignition wires, spark plug fouling, and overheating of cylinder heads. The pilot moves the propeller controls to high RPM position. Ignition switches are checked at moderate power and with the turbo controls still in the off position. The co-pilot tries the left magneto and the right magneto individually to see that all spark plugs are in operation. This must be done quickly to prevent gases gathering in the exhaust stack and backfiring. Backfiring can cause serious damage to the nozzle box of the turbo-supercharger. After calling the control tower on the radio, the pilot taxis to the takeoff position. Each engine is run up individually. The pilot opens the throttle fully and increases power by moving up the turbo-supercharger regulator. If the turbo control travel was carefully pre-adjusted, this need not require further prolonged ground run-up. Moving up the regulator control causes the regulator to close the wastegate on the nozzle box of the turbo-supercharger. This forces more of the hot exhaust gases out through the turbine wheel, causing it to speed up, and thereby causing more air to be fed to the engine. When desired takeoff manifold pressures have been reached, the pilot locks the turbo controls. He then closes the throttle. Note that he has left the turbo controls in the high boost position. This is done only in taking off and landing. At all other times, the turbo controls should be off before closing the throttles, and the throttle should always be opened before the turbo controls are advanced. Ready for takeoff, the pilot calls the control tower. Receiving his clearance, he slowly opens the throttles to the full position. The airplane picks up speed and takes off. When about 500 feet altitude is gained and the airplane has ample speed, the turbo regulator may be retarded, and if further reduction in power is desired, the throttle is retarded and engine speed reduced to desired cruising or cruising climb power. At the proper time, as the objective is approached, following flight instructions, the pilot starts the plane climbing to higher altitudes. The co-pilot makes sure that the booster pumps are on and adjusts propeller pitch control to desired RPM. Then he opens the throttle to full open position. And the pilot sets the turbo regulator control to maintain required manifold pressure. As the airplane heads up into the rarefied atmosphere, the crew puts on their oxygen masks. As altitude increases, it is necessary for the pilot to occasionally adjust the turbo regulator in order to maintain desired manifold pressure, because the turbo becomes more efficient as the airplane climbs to higher levels. This is always done with the throttle fully open. Reaching about 25,000 feet, the possibility of interception and danger from anti-aircraft fire are greatly reduced. The pilot levels off and retards power until the airplane is flying at the best speed for bombing. The bombs are dropped and the airplane starts home. The pilot, warned of enemy fighters, increases the propeller speed to maximum allowable. At the same time, the co-pilot takes over the flight controls and climbs. The throttles are opened wide, and the pilot then advances the turbo regulator control to give full military power. The big ship heads toward higher altitudes where it can outperform the enemy fighters. As the airplane passes approximately 27,000 feet, the pilot should retard the turbo-supercharger control at a rate of about 1 inch of mercury manifold pressure per 1,000 feet of altitude. At about 30,000 feet, the pilot levels off. When he feels that it is safe to descend, He reduces power by retarding the turbo regulator and reducing engine speed to a lower RPM. To further reduce power, the pilot retards the turbo regulator. At the proper time, oxygen masks are removed. Co-pilot moves the mixture controls to automatic lean and switches off the fuel booster pumps. Nearing their base, the pilot opens the throttle and with engine set for maximum cruise RPM, sets the supercharger controls to obtain rated manifold pressure. This gives the pilot ample power to go around again if an emergency should arise during the approach for landing. The wing flaps are lowered and the airplane rolls to a safe landing. Control of the turbo-supercharger on pursuit-type airplanes is much simpler, since the throttle and turbo regulator may be combined. The pilot may then have only one power control to operate. It is still necessary that the pilot should reduce manifold pressures at altitudes above 25,000 feet to prevent seriously overspeeding the turbo-supercharger wheel. The turbo-supercharger will furnish a bonus in power at high altitudes. If you operate it properly during the many hours of normal service, it will respond in a life and death emergency, answering every demand you make on it, and give you power over and above the best of our enemies. Ride this master of the skies to victory. A heavy bomber squadron takes off on a long-distance operation against the enemy. Flying with great speed at high altitudes, they avoid detection, drop their loads, and are off for home before enemy fighters and pursuit planes can possibly climb 25, 30,000 feet or even higher. In these cold substratosphere regions of the sky, where the air is so thin it affects engines as well as men, the fastest enemy planes are no match for our B-17s or our B-24s, which return safely to their bases.
Air supremacy is a vital factor, perhaps the deciding factor in this war. The achievement of air supremacy involves speed, personnel, firepower, and maneuverability. But one of the most important factors is the ability to achieve maximum altitude without the loss of power. The Civil War maxim of getting that fastest with the mostest men can be revised in the terms of military aviation to getting up highest with the mostest fighting power.
This master of the skies, the dynamic turbo-supercharger, is the reason for our air superiority at high altitudes. For the year 1941, the Collier Trophy, one of the highest honors in aeronautics, was awarded jointly to Dr. Sanford A. Moss and the Army Air Forces for 25 years of collaboration in perfecting the turbo-supercharger, which is playing a leading role in sweeping our enemies to defeat. The turbo-supercharger makes possible high-altitude flying with full engine power. An airplane engine derives its power from explosions of a mixture of air and gasoline. At altitudes above sea level, the air gets thinner and thinner. Therefore, these explosions get weaker and weaker. At 20,000 feet, an unsupercharged airplane engine gives but 1/2 its normal power. At 35,000 feet, only 1/4 of its power. The turbo-supercharger counteracts this loss of power by compressing and cramming air into the engine, thereby maintaining proper manifold pressure to give full power at high altitude. It performs the same service for engines that oxygen equipment performs for pilots, kidding the engine into thinking it is always working at sea level. Without a turbo-supercharger, the engine gasps for breath. During World War I, the first model turbo-supercharger was tested under great difficulty. On a truck, at the summit of Pikes Peak, 14,100 feet above sea level. The Liberty engine developed 400 horsepower at sea level, but moving up to 14,000 feet, it dropped to 265 horsepower. Then the turbo-supercharger not only boosted it up to 400 horsepower, but to 410, or 10 more than normal at sea level. The turbo-supercharger has demonstrated its worth in actual combat all over the globe. Our great bombers, the Boeing B-17 Flying Fortress and consolidated B-24 Liberator, together with the Lockheed P-38 Interceptors, the P-43 Lancer, and the deadly Republic P-47 Thunderbolt, are all turbo-supercharger equipped, which enables them to fly and fight effectively at great heights above the earth. Our turbo-supercharged interceptors and pursuits can get on top and stay on top of anything the enemy has to offer. These tactical advantages are the key to air supremacy and ultimate victory. Turbo-superchargers permit our bomber pilots to avoid bad weather, even storms, by climbing over them, making it possible to fly at altitudes and speeds which result in maximum engine efficiency. Obviously, we have a decided edge when we can bomb the enemy with a minimum of danger to our planes and personnel. Flying turbo-supercharged planes, our boys have bombed enemy objectives with amazing accuracy from heights where they were invisible and unheard from the ground. There had been no warning sirens, no opportunity to take shelter, only the sudden scream and paralyzing crash of bombs falling out of a clear sky. Almost without exception, these planes have returned safely from their missions. Time after time, you have read of our big bombers returning unscratched from perilous raids in all theaters of the war. It is true that our heavy bombers have been in dogfights, have suffered casualties in men and planes, but in practically every instance, this has happened when planes were operating at levels below 25,000 feet. Another reason we have to get up higher and higher is to get above the effective range of anti-aircraft fire, which has been reported even above 30,000 feet. All combat planes are equipped with gear-driven superchargers, which are built into the engines and driven from the engine crankshaft. These geared superchargers are effective up to medium altitudes. At high altitudes, the turbo-supercharger is needed to provide additional pressure to maintain full engine power. With proper care in installation, maintenance, and operation, the turbo-supercharger is extremely effective, reaching its full power and efficiency at 25,000 feet or higher. This is the turbo-supercharger installation in the B-17. Installations vary according to the different types of ships, such as the B-24, the P-38, the P-43, and the P-47, where it is submerged in the fuselage. A turbo-supercharger is driven by the terrific impulse of hot exhaust gases from the engine. It largely uses waste power. Waste exhaust gases pour into the nozzle box, where they are directed onto a metal windmill or turbine wheel at 1,500 degrees Fahrenheit, with all the red-hot energy that implies. This blazing force spins the turbine wheel at terrific speeds, up to about 20,000 revolutions per minute. The turbo-supercharger stands the gaff of almost impossible high-speed strains and stresses, and still performs its task at temperatures ranging from 1,500 degrees above to about 67 degrees below zero Fahrenheit. The basic principle of all turbo-supercharger installations is outlined in this diagrammatic drawing. Flexible joints are installed between the component parts to absorb vibration. For purposes of clarity, we will divide the system into 5 parts. 1, the induction system. 2, the exhaust system. 3, the ventilating or cooling system. 4, the control system. And 5, the lubrication system. Individual installations vary according to the different design of ships, but their functions remain the same. The induction system comprises rammed air intake in the engine nacelle or in the leading edge of the wing. The speed of the plane rams air into these intakes and assists in keeping up pressure. Ducts carry this air to the compressor, where it is compressed and forced through the intercooler, and the carburetor to the inlet of the geared supercharger. The geared supercharger is used to do part of the required supercharging and to improve the distribution of the fuel charge to the cylinders. The exhaust system takes the high-temperature exhaust gases from the engine to turbine wheel, or out through the wastegate to the atmosphere. The cooling or ventilating system cools the supercharger parts, thus preventing damage due to the high-temperature exhaust gas. Rammed air is carried through ducts to the turbo, where the stream is split by the baffle plate and cool air forced against the bearing housing, compressor casing, the back of the turbine nozzle box, and the back of the turbine wheel. Other ducts perform the same functions in relation to the exhaust stack shroud, which insulates the exhaust stack, and the air intercooler, which for proper combustion reduces the temperature of the air fed from the compressor to the engine. The intercooler cools air in the same way the radiator on your car cools water. The cooling cap supplies air to the rim of the turbine wheel to lower temperature of the wheel disc. The turbo-supercharger is controlled by a hydraulic regulator, which operates the wastegate in response to pressure changes in the exhaust stack. The wastegate control is adjusted by a boost lever in the cockpit. The wastegate controls speed of the supercharger by bypassing the gases around the wheel. With the wastegate open, the turbine will idle. Closing it by degrees enables the turbo-supercharger to operate at required speeds. Lubrication is accomplished by a gear-driven pump. One element of the pump takes oil from the tank and supplies it under pressure to the moving parts. The second, or scavenging element, returns the oil to the tank. Like every other part of a modern military airplane, the turbo-supercharger must be understood by pilots, who should remember important instructions regarding control. Before starting the engines, be sure that the turbo-supercharger is in the off position. No provision is normally made to supply engine air except through the turbo, its ducting, and intercoolers. Therefore, considerable resistance will be imposed on airflow to the engine when the turbo regulator is in the off position. In order to obtain sufficient manifold pressure for takeoff power, it is necessary on some airplanes to use a small amount of turbo boost. Close the wastegate a little. Tactical requirements may dictate using military-rated power for a period not exceeding 5 minutes. Climbs are usually made with about normal rated power. Small adjustment of the turbo control may be necessary during climb to keep manifold pressure at desired level. For low altitude, low power cruising, when the geared supercharger is enough to provide proper manifold pressure, reduce engine throttle to maintain the desired manifold pressure. At high altitudes of more than 20,000 feet, it is not practicable to operate at very low engine speeds and powers. Turbo superchargers should be kept engaged at all times when induction system icing may be encountered. Above approximately 25,000 feet, manifold pressure should be reduced in accordance with the instructions given for each type of plane to avoid overspeeding the turbo supercharger. For gliding and approach for landing, the turbo regulator is set approximately at maximum cruise position to ensure power to go around the field again if necessary. The performance of ships equipped with turbo superchargers is a matter of teamwork between ground crews and pilots. It is not necessary for a pilot to learn all the mechanical details of construction, but it is wise for him to know what he can expect from a turbo supercharger when he needs its assistance to win the fight, save the lives of his crew and himself. The men who fly these powerful planes are going to depend upon their turbo superchargers in emergencies which will test all their skill, strength, and courage. Operation and control are largely automatic, But there are certain times when the pilot needs power and needs it instantly. These times occur under stress of actual combat conditions, and his reaction should be instinctive. The pilot will depend upon this master of the skies to give him the edge of speed and maneuverability, which means the difference between defeat and victory in the substratosphere regions of the sky. It is with enormous pride in American scientific invention and mechanical ability. Look at our interceptors and pursuits, which can get on top of anything that flies. It is with a feeling of grim satisfaction that we know our bombers are able to shoot down or escape from anything the enemy can put in the air. But this edge is held only as long as the turbo-superchargers on each and every one of these planes is kept at the peak of performance. They must answer every demand that the pilot makes. It's up to the ground crews to keep them flying, and flying higher and higher. Ride the master of the skies to victory.
One problem facing the designers of the next generation of turbojet engines is that of increasing turbine inlet temperatures. Air-cooled turbine blades may offer a solution to this problem. The fabrication of a cast air-cooled turbine blade that has shown promise in prototype testing will be shown in this film. This blade was made using a modification of the lost wax casting technique. A process to provide long, slender holes for cooling passages was developed by the Lewis Flight Propulsion Laboratory of the National Advisory Committee for Aeronautics. This development is particularly important because the superalloys used in aircraft turbine blades are extremely difficult to machine. Ceramic tubes are used as part of the casting mold to establish cores or holes through the turbine blade casting. Core tubes of the desired outside diameter are assembled in a pattern die. The core tubes are held in place by embedding them in a bar of soft wax using a hot wire or knife. The dies used are made of a low-melting alloy cast around a brass master pattern. A casting pattern is made by closing the dies containing the ceramic tubes, clamping the dies in a wax injection machine, and injecting molten wax under pressure. The wax pattern containing ceramic tubes is removed from the die, and excess wax is trimmed, leaving a light wax film on the exposed ceramic tubes to permit freedom of movement due to expansion. Additional pieces of wax are assembled by welding with a hot wire. These pieces will form sprues, runners, and ingates or passages for the molten metal to reach the blade cavity in the casting mold. The assembled wax is mounted on a waxed base to seal it. A can-type flask is placed over the assembly, and it too is sealed at the bottom. When the investment is thoroughly mixed, it is poured into the flask and around the wax pattern assembly. The flask is then placed in a vacuum chamber to remove air from the mix. After investing and air drying, the molds are placed in a furnace. Here the drying is completed, the wax is melted out, the wax residue is burned off, and the mold is cured. During this furnace cycle, the temperature is gradually increased from room temperature to 1900 degrees Fahrenheit. Metal alloy for the casting is melted in an electric induction furnace. When the metal reaches a temperature of 3000 degrees Fahrenheit, the crucible of molten metal is placed in a centrifugal casting machine, and the hot mold is placed over it. As the casting machine is spun, the molten metal is thrown into the mold. The casting is removed by breaking away the mold. After the casting is cleaned up, the ceramic tubes used to form the cooling passages in the blade must be removed. This is done by threading fine stainless steel wires through each ceramic tube and stretching them taut on a frame. The turbine blade is then attached to a cam device designed to slide the blade up and down on the wires. The lower part of the assembly is then immersed in a bath of molten caustic. This helps to remove reaction products and introduces fresh caustic to the bore of the tubes, and hence accelerates the solution and removal of the core tubes. The rough casting is cleaned in an air-water abrasive blast. A suitable base configuration is then ground, and the blade is ready for testing in a research facility. The process you have just seen illustrates a principle that has been effective in producing long, thin-cored holes in casting.